Alright guys, I have here a review problem dealing with energy conservation and rotational motion. So let's take a look at this picture that I made. So this is about a trapeze performer, a circus performer who is holding onto a trapeze. You can see that the trapeze is 10 meters long. The trapeze has a metal bar at the bottom that is 20 kilograms and it has a radius of 5 centimeters. The person is with the arms extended is 2 meters long, and the center mass of the person is 1 meter from their feet, and the mass of the person is 50 kilograms. The trapeze is making an angle of 45 degrees with the vertical, and the question here is to figure out how fast are the feet of the performer going when the performer is at the bottom of the swing. Okay, so the performer holds on to the trapeze, they swing together down, and the question is how fast are the feet of the person moving at the bottom. So what's the plan to solve this problem? So first we're going to start by modeling the person as a rod. Okay, so this is an approximation. So the body of the person with the arms extended, we're going to model that as if it was a uniform rod. We're going to find the moment of inertia of that object with respect to the axis of rotation. Then we're going to find the moment of inertia of the trapeze. Then we're going to add the two moments of inertia to get the total moment of inertia of the system, because as the person is swinging, holding onto the trapeze and person are moving together as a rigid object. So the total moment of inertia of this rigid object is important, and we're going to use that value to set it up in an equation of conservation of energy. So the conservation of energy equation is going to allow us to find what is the angular velocity at the bottom of the swing. Once we have this value for the angular velocity, we can use the relationship between omega and a tangential speed, between the angular velocity of an object and the tangential speed at some point on that object, and this equation is going to allow us to find what's the velocity of the feet of the person. So that's the idea. So starting with now the moment of inertia of the person. So the person is 2 meters long. As I said, we're going to model the person as a uniform rod. The center of mass of the person is 1 meter away from the trapeze bar and from the feet of the person, since the person is 2 meters long. And since the person is a rod, the moment of inertia of a rod, if you remember, with respect to the center of mass is 1/12 the mass of the rod, in this case the person, times the length of the rod squared. There's a picture here again of the person. So 2 meter long rod, center of mass 1 meter away. So the L here in that equation, L refers to the length of the rod. So L will be, we will be plugging in 2 meters. However, the moment of inertia of the person is not just this 1/12 term, because the person is not rotating with respect to the center of mass. The rotation of the person is happening as the person and trapeze swing. The rotation is happening with respect to the pivot point, which is the end of the string, whatever point the string is attached to. So the equation for the moment of inertia includes a term when the axis of rotation is not at the center of mass of the object, but some point away, a distance d. The equation for the moment of inertia, we need to add the term in red, md squared. So m is the mass of the person in this case, and d is the distance between the center of mass of the object and the pivot or axis of rotation. So we're dealing with the d for the person, and as you can see there, the distance must be 11. It will be 10 meters for the length of the string, and then 1 meter from the string or from the trapeze bar to the center of mass of the person. There's another that's another 1 meter. So for a total of 11 meters, the distance between the center of mass of the person and the pivot point. So this equation, so that's 11. So the equation that we're going to use, this equation over here, maybe you remember the name of this equation. We're using the parallel axis theorem. That's what we're using here. So with this equation, we're going to be able to find the moment of inertia of the person with respect to the trapeze attachment point. So plugging in the numbers, we have 1/12, mass of the person is 50 kilograms. The length of the person is 2 meters. that goes squared. And we're going to add the mass of the person, 50 times the distance between the center of mass and the pivot, which is 11 meters square. And plugging in the numbers, we get that the moment of inertia of the person with respect to the pivot is 6,066.7 kilograms meter square. All right. Now we move on to find what's the moment of moment of inertia of the trapeze. So the trapeze is a rod or a cylinder, and again the parallel axis theorem tells us that we can find the moment of inertia of that trapeze rod as a moment of inertia with respect to its center of mass plus the term md square. So we're going to replace the numbers here for that rod. The rod is a cylinder. So for a cylinder, the moment of inertia for an axis that goes through the center of the cylinder along the axis of the cylinder, the moment of inertia is 1/2 of md square. Cylinder or disc, the same geometry. So 1/2 of mr square, where r is the radius. That was given in the statement of the problem as a 5 centimeter rod for a radius, and we have the term md square, where d is going to be 10 meters. That's the distance between the center of the cylinder and the pivot, the point where the string is attached to some solid object. So replacing the numbers, we have 1/2 of 20 kilograms times 0.05 meters. Remember that you have to use MKS units. So 5 centimeters needs to be converted to meters. So that's 0.05. You square that. And we're adding the term mass of the bar, 20 kilograms, times the distance between the center of mass of the bar and the pivot. That is the length of the string, and that's 10 meters. So plugging those numbers in, we get about 2,000 kilograms meter square. Notice that the first term, the moment of inertia of the bar with respect to its center of mass, is very, very small. So we can neglect it. It's less than 0.01. It's less than that. So it's 0.025. So in any case, that's pretty small compared to 2,000. So we're just going to round this to 2,000 kilogram meter square. So what's the total moment of inertia of the person plus the trapeze? The person we just found before, it was 6,067, and the trapeze, basically the bar of the trapeze, 2,000. So for a total of 8,067 kilograms meter square. So we have a total moment of inertia of the object that is rotating. That is the trapeze and the person together. They have a combined moment of inertia of 8,067 kilograms meter square. So now we're going to move on to examine the problem from the point of view of conservation of energy. So the forms of energy involved as the person swings down, holding onto the trapeze, is gravitational potential energy and kinetic energy of rotation. So the total energy of the system, we're going to neglect, of course, as usual, air resistance. So the mechanical energy, the sum of these two forms of energy, is going to be conserved. So there is no change in the mechanical energy of the system. So delta E is equal to 0. So that means that the change in the gravitational potential energy is going to be the negative of the change in the kinetic energy. So if the person and the trapeze, if they lose gravitational potential energy, they will gain that same amount of energy. They will gain it in the form of rotational kinetic energy. So this is another way to say that the initial energy equals the final energy, as explained before in several videos. So we're going to take a look now and see how much gravitational potential energy does the trapeze lose and the person. So the trapeze's center of mass is there initially. The center of mass of the person is indicated by this line initially. And after they swing all the way down to the bottom of the swing, the center of mass of the trapeze has moved to this new location that you can see there. The center of mass of the person is at a new location. And we can figure out how much is the drop in height for the center mass of the trapeze and the person by using the fact that the center mass of the trapeze is 10 meters away from the pivot, from the center of the rotation, and the center mass of the person is 11 meters from the axis of rotation. So we're going to use that to calculate the change in the potential energy of the trapeze. So the trapeze is going to lose an amount of potential energy equal to the mass of the trapeze times g times the height that the trapeze drops, the amount that it drops, basically this amount, this amount over here. That has been, we already dealt with this issue about what is the height that a pendulum drops. So if you review those videos, you will find the equation that the amount that the pendulum drops is the length of the pendulum multiplied by 1 minus the cosine of the initial angle measured from the vertical. So so using that, if you don't know what I'm talking about, please review your notes, the videos that we dealt with the conservation of energy for a pendulum. So plugging in the numbers, we get the change in the gravitational potential energy of the trapeze. So plugging in the numbers, you get minus 574.1 joules. For the person, we're going to have a similar equation. It's going to be minus the mass of the person times g times the length or the distance between the center of mass of the person and the pivot, that's 11 meters, and then the term 1 minus cosine of the initial angle, which is 45, so 1 minus cosine of 45. Plugging in the numbers, you get the person drops 1578.7 joules of potential energy. So the total change in the potential energy of the system being made of the trapeze and the person, is minus 2152.8, adding those two numbers. So all of this energy is going to be converted to rotational kinetic energy. So we're going to gain an amount of rotational energy equal to 2153 joules, just to round it to 4 significant figures there. So this increase in kinetic energy of rotation is going to be the final kinetic energy of rotation, 1/2 of the total moment of inertia times the final angular velocity square, minus the initial rotational kinetic energy, which is 0, because the person and the trapeze were not moving at the initial moment. When the person just holds on to the trapeze, the person is not moving, the trapeze is not moving. So the change in the kinetic energy is 2153, and that's the same as the final rotational kinetic energy. So replacing the total moment of inertia, which we calculated previously, 8,067 kilogram meter square, we can solve for the final angular velocity of the trapeze and the person. So solving for omega final square, and then taking the square root of that, we get that the final angular velocity, the angular velocity at the bottom of the swing, is 0.73 radians per second. So now we're one step away from our final answer, because now we have the angular velocity of the system, trapeze and person moving together. We're looking for the speed of the feet of the person. So when an object is rotating with a particular angular velocity, different points on that object are going to have a different speed, and that speed is going to be determined by how far is the point from the axis of rotation. So since we're talking about the feet of the person are 12 meters away from the axis of rotation. So all we have to do is take the angular velocity, multiply by 12, and we get our final answer, 8.77 meters per second. That's how fast the feet are moving at the bottom of the swing. Alright guys, that's it. See you in the next one.